So hello and welcome student to the previous lecture, and this is course number MA412 linear algebra, and this is lecture number 24. Okay, now recall last class we defined the notion of orthogonality and orthonormality. Okay, so we said two vectors are orthogonal if the inner product of these two is 0, and a set is orthogonal if any two distinct vectors. So okay, so we will write down here distinct vector are orthogonal. Okay, and in addition, if each of the vectors has norm 1, then we call it orthonormal. Okay, this is called orthonormal, or in that sense you can say that suppose we have a set S, maybe of this form something, and then you will say that orthonormal means the inner product of Vi Vj equal to delta Ij. Then we say that this is orthonormal. Okay, so when I equal to j is 1, otherwise is 0. Okay, then we say that this is orthonormal. That we define. Now maybe we can describe this with an example. Okay, so let me give an example here. So recall that we discussed C0 2 pi space of continuous functions over complex valued space of complex valued continuous functions over 2 pi. Okay, and then remember, recall that we define the inner product. What are the inner products? So take two map f and g, and we define inner product by 2 pi 0 to 2 pi fx gx bar complex conjugate with dx. Okay, so this was the inner product, and obviously this is inner product easy to prove. Okay, so with respect to this V becomes an inner product space, and one can ask whether we have some kind of orthogonal or orthonormal subset or not. Okay, so for that let us try to find out such example. Okay, so maybe let me start and set S, which is a collection of say functions where you choose in positive integer or any integer, rather any integer. Okay, and where this f of n is defined by this f of n of x is defined by e power I in x. Okay, obviously 0 less than equal to s less than equal to 2 pi. Okay, so this is the definition of fn. So obviously this clear that fn is continuous functions on close interval 0 1 as 0 to 2 pi, and so one can ask whether this fn's forms orthogonal set or orthonormal sets. So we can check what happens if you try to find out the inner product f of m with f of n. Okay, and that will gives you 1 by 2 pi 0 to 2 pi. Okay, and then f of Okay, so if m of x, if n of x bar dx, okay, and that is nothing but 1 by 2 pi 0 to 2 pi, and this one is e power I m x and e power I n x whole bar dx. Okay, now the complex conjugate of e power I n x is nothing but minus of I n x, right? So this will gives you 1 by 2 pi 0 to 2 pi e power I m x into e power minus I n x dx, and that is equal to 1 by 2 pi 0 to 2 pi e power I m minus n x dx. Okay, now if you now this is a simple integration. Now if you do simple integration, you will see that whenever m not equal to n, okay, so this is in general. So if now what happens if you n not equal to n, so then obviously you can do integration of, and then that will become 0. We just do it if m not equal to n. Okay, in the case when if m equal to n, then whatever, then the integration of the inner product of this will be 1 by 2 pi integration 0 to 2 pi, and m equal to n means 0, so this is dx, and hence you have 1, right? So what does that mean? That means integration of inner product away from n is nothing but the Kronecker delta, and hence is an orthonormal subset of V, right? So obviously you can this is obvious that this is infinite, so you can find out infinite orthonormal or orthogonal set also. Okay, now interesting thing is that this orthogonality has many properties. Okay, and some of the properties we can actually prove here, and one such property is it's called Pythagorean's theorem or Pythagoras theorems. Okay, whatever. So theorem Pythagorean theorem. Now, I hope everybody knows it from their school. So if we have, say, for example, if you have a right angle triangle, then this base square plus the side square equal to hypotenuse square, right? Now we can think this thing in differently. You can write down by this. Suppose you have a vector here which is say x, and then you have a vector here which is say y, and then obviously this vector will be x plus y. So what is the version of Pythagorean theorem here? So the length of these vectors, okay, whole square, that is norm, right? The distance become the length become norm here. The norm of x square plus norm of y square should be equal to norm of x plus y square. Okay, and you see that here these two are actually perpendicular, which we call this orthogonal. Okay, so what is the theorem here? So if to suppose, so let x and y belongs to be two orthogonal vectors, then what happened? Then we have this norm of x square plus norm of y square, that should be equal to norm of x plus y whole square, right? This is the Pythagorean theorem, right? So this vector is x plus y and the length will be norm of x plus y. Okay, so the proof is not difficult, it is rather simple, so let me write down quickly. So we start with this norm of x plus y square, and by definition this is inner product of x plus y comma x plus y. Okay, now we'll use the properties and the reference inner product that gives you x and then yx and then xy and then inner product of y, right? Now you see that as x and y are orthogonal, so both this and this is 0, right? So we get what? We get this is nothing but norm of x square, this one is norm of y square, right? And this portion 0 and this inner product of xy equal to 0, which is equal to inner product of yx. The simple proof of Pythagorean theorem, and this is true for all xy which are actually parallel to each other. Okay, sorry, which are perpendicular to each other, means orthogonal to each other. Okay, so this theorem is called Pythagorean theorem, and obviously which is general version of Pythagorean theorem, and then it's very rather easy to prove. In fact, for art in school in geometry we have learned this theorem rather lengthy proof, right? So now we want to discuss one more interesting theorem here, and that is called parallelogram law or parallelogram theorem, whatever you call it. So theorem parallelogram law. Okay, what is that? So you start with a inner product space, whatever, and suppose you have two vectors. Okay, so let xy belongs to V, and I mean this is any two arbitrary vectors. So this is you don't have to check that whether x and y are perpendicular or not, like orthogonal or not. Okay, for any two vector, this is always true. So we take norm of x plus y whole square plus norm of x minus y whole square, and that will be equal to 2 times norm of x whole square plus 2 times norm of y whole square. Okay. So before going to the proof, let us try to understand why it is called parallelogram law. Now you see that suppose you have a parallelogram and the sides are say x, vector x and vector y, and then you just complete the parallelogram. Okay. Then x plus y will be this. Okay. And x minus y will be this. Okay, and that tells you that the length of this vector, which is actually diagonals. Okay, and length of this vector, if we add those things, that will be 2 times length of this plus length of this, and this is obvious in the sense that you can use triangle law, obviously. For example, in this small triangle, you see that this x plus y, this is x, this is y. So, I mean, I'm giving that geometry idea. Okay, you can use that Pythagorean theorem, I mean the triangle law, that this plus this equal to this of this form also. Okay, and obviously x and y are perpendicular, then from Pythagorean theorem you can get easily, right? Now anyway, so how do you prove this? So proof is also not so difficult. So you start with this norm of y square plus norm of x minus y square, so which is equal to x plus y, and here you will have x minus y, okay. Now from the first inner product you will have x plus, so inner product of x plus yx plus xy plus inner product of yy. Okay. The second you will have x6 and minus yx and then minus xy plus yy, right? And this will get cancelled. And you'll have 2 times of this xy. This is nothing but 2 times norm of x square plus 2 times norm of y square, right? So this parallelogram law also true, that you can easily find out from the idea of inner product. Okay. So there are many such equation ideas or identities too. Maybe we'll discuss later some of those. Okay. So now let me discuss one more important idea, that whenever you have a norm is given, then you can define something called metric distance, and from the distance you can actually there are many ways you can, obviously there are many other identity you can prove, but there are something called polar identity, other things. Some of those things you may find out inside your tutorial session. Okay. So, one of such distance I just want to discuss, that whenever you have inner product is given, so equation, so maybe I should define what do you mean by that. So let you have a vector space, and the norm may be coming from inner product or not, doesn't matter, but I have defined norm, okay, in the previous classes. And maybe I guess, let me write down norm linear space, normed linear space. Okay, then you can define define something called metric. So we'll call dxy the metric. This is called metric, what is nothing but the generalization of the distance. So this metric, which is y norm of x minus y. Okay, so this is called the metric, which is nothing but the which is the generalization of, which is a generalization of distance. Okay. Distance, or rather you can say that, yeah, distance. So what are the important idea of this definition, that it satisfies few properties, and properties are almost easy maybe here. So what are the properties satisfied? First of all, that this distance or the metric, it cannot be negative, it always non-negative, means it can be 0 or positive. Okay. And then second property, or rather you can say that here, that this is 0 if and only x equal to y. Okay, only one case, and this is always symmetric, symmetric, symmetric. Okay, number 3, there is something called triangle inequality. What does that mean? That means that d of xy is less than equal to d of x, z plus d of z, y. So what does that mean? That means if we have 2 points here, x and y, if you want to get the distance, and suppose you have another point z, then sum of this and this, so the distance from x to y and x to z and z to y, if we add up those distance, that will be bigger than this distance. And this is the simple equivalent geometry. You have learned this thing in our school also. Okay, so that is exactly triangle inequality. Okay, the proofs are simple. Obviously, by definition, norm is always non-negative. So first property is obvious, and norm of this is 0 if only x equal to y, right? This is obviously 0. Symmetry property also is coming from the fact that the norm of x minus y and norm of y minus is the same. And similarly, triangle inequality is coming from the that triangle norm. Okay, so these are simple. Now, so this is an interesting idea that maybe we will learn more in next semester in topology and function analysis. Okay. So now coming to the some more properties of this orthonormal. Okay, so some properties. Of orthogonal this set. Okay. Now this is a natural question: is that what is the importance of orthogonal set, and what is the connection between orthogonal set with linear independent subset of a vector space? Okay. The answer is that whenever so theorem. So let me write down as a theorem. Let be an inner product space. Okay, then and choose say a subset of V be a orthonormal set. Okay, and such that 0 does not belong to that, obviously. Otherwise, I can claim be an orthogonal set consisting of non-zero vectors. Okay, consisting of non-zero vectors. Okay, then S is linearly independent over the same field with the field where V is defined. Okay, linearly independent over the same field. So I did not mention field here, that's why I'm not writing, but it should be over the same field, say over F, and this V over F I must mention here. Okay. Okay, so I did not assume that F is finite or infinite, doesn't matter. So only thing is that to prove something is infinite. So for example, if you want to prove that a infinite subset is linearly independent, it is enough to prove that every finite collection of that set is linearly independent. Then I am done, right? So proof is what? Then you start with that. So proof. So I don't know whether this is finite or not, but I can always choose finitely many collection and check that for each such finite collection it is linearly independent. Then I am done, right? So let you choose something, say v1, v2, vk as subset of the any arbitrary. I am choosing arbitrary subset of S, and what is given that S is orthogonal. See, S is orthogonal. So what does that mean? That means then but you know that vi ej equal to 0 if I not equal to j, and if I equal to j, then this is norm of vi square, right? I not equal to 0. This is known to us. Okay. So now once we know this thing, then I can check whether this is a linear independent subset or not. Then I am done, right? This is arbitrary subset. So what does that mean? That means every finite collection, finite subcollection of S is linearly independent, and hence S will be linearly independent, right? So to check if it is linearly independent or not, what you know? So let we start with a linear combination. So let there be some constants c1, c2, ck belongs to f, such that or assume, you can say that, assume that whatever, such that what happened, such the summation ci vi equal to 0. Now suppose if there exists such sets for which this thing happens, then what happens? Then you can so what is your goal? So your goal is to prove that all those CIs, so let me write down this properly, formally, I equal to 1 to k, and your goal is what? Your goal is to prove that all such CIs are actually 0. Then I am done. And what is given to me? The property what is given to us that inner product of vi vj's are actually 0 whenever I not equal to 0, right? That is given to us. Now can we apply this theorem? Can we apply this property? This simple question. The answer is yes, we can apply this property. And so let us check how to apply. So what we will do, so we will take the inner product of then, so now we are taking inner product with taking, say, inner product with Vj, we get, what do we get? We get this inner product summation ci vi I equal to 1 to k, and vj, this is 0, right? Because the sum was 0, and if you take inner product with the 0, then you will always 0, right? But this property you have to learn. So this will be linearity in first argument tells you that this is nothing but summation ci inner product of vi vj I equal to 1 to k, which is equal to 0, right? Now because vi vj's are orthogonal, so the sum will survive only if when I equal to j. So when I equal to j, you will have cj and inner product of vj, which is equal to 0. But recall that this is cj and norm of vj square equal to 0. but I choose my A such that there is no non-zero vector, right? So what does that mean? That means the norm of Vj cannot be 0. So this norm of Vj cannot be 0 because all the vectors of S are non-zero vectors, and norm of any element will be 0 if and only that is 0 element, right? So this implies Cj equal to 0, and this is true for Fdj for all j equal to 1, 2, and k, right? What does that mean? That means any finite subset of, so thus any finite subset of S is linearly independent, hence S is also linearly independent. Okay, so this is a proof that you can always say that you can always say that whenever you have orthogonal set, that has to be linearly independent, right? Now, so now at this point we can actually define something called orthonormal and orthogonal basis. And what is that? So definition. So an orthonormal basis of an inner product space is an order basis which is orthonormal set. Which is orthonormal set. Okay. So maybe we can give some examples. So you start with say R2 is equal to R2 or other, yeah, so maybe equal to R2 and say R2 you check that the standard basis just say 1 0 0 1 is always orthonormal. This is simple, right? This is orthonormal. But you have many other example also, and you check that, for example, say basis 1 1 by root 2 1 1. Okay, so this is now 1 obviously, and then you check 0 1. Yeah, so this is also orthonormal basis. Okay, this basis is also orthonormal. Okay, so there are many ways you can actually no 1 minute. No, this is not orthogonal, so I have to find out something which is orthogonal. Okay, so what will be orthogonal to this? I think 0 1 minus 1 probably, yes, 1 by root 2. You check it. So if you take inner product, so this is 1 and 1, yes. So 1 minus 1 and 1 by 2. This is orthonormal. Okay, this is orthonormal. Okay, so this is an example. Now it has, you can actually say many more properties whenever you suppose you have a basis which is orthogonal. Okay. So in general, we can have some theorems. So let me start with general theorems, and then we can talk about specific theorems. So suppose so let be this be an inner product space, and suppose we have a maybe say eliminate B, so we have some vectors here, so B1, B2, Bk, B and orthogonal. So I'm just taking orthogonal subset, I'm not taking basis. So this is general theorem, so it is true for basis also. Orthogonal subset of so non-zero vectors. So 0 I cannot take. 0 is orthogonal to every vectors, but 0 I have to avoid, otherwise these vectors will be linearly dependent, right? Non-zero vectors. Okay. Now, if you choose an element, say x, element of, say for example, it is inside span of B, then what happens? Then you can actually write down x in terms of these vectors that we know, but you can say actually what are the coefficients. So then actually x can be written as summation the coefficient x in a product of x in a product of this vi, okay, and then norm of vi square with vi, okay, I equal to 1 to k. So these will be the coefficient actually that you can find out in terms of inner product. This is the so much advantage in a inner product space, and that is in general vector space you cannot see, right? So this kind of coefficients are also, I mean, we will define it, that they are called Fourier coefficients also, okay, we'll define later. So how to prove this kind of theorem? The proof is also not very difficult. So what happens? So because your x belongs to this span of B, so we can find out, and we find out some constant such that x is a linear combination of those vectors, right? So let C1, C2, Ck belongs to F such that your x can be written as summation Ci Vi I equal to 1 to k, right? This is by definition that x is element of span of Vi, so that B, okay, and element of B are V1 to Bk. So this is, you know, so then from here what you can say that this is true for any I equal to 1 to k, right? Now if you choose any j, and then if you want to take inner product of x with j, then it will be having of this form, right? Inner product of this summation Ci, Vi and Vj, and your I is sum 1 to k. Okay, this is true for all j equal to 1 to up to k for all, right? Now in particular, if you use the property of inner product, then you will have this one will be what? This one will be summation of Ci and the inner product of Vi and Vj, where I is 1 to k. Okay. Now because your A and your set this is orthogonal subset, so you know that only when I equal to j it will serve, otherwise it is 0, right? So it will be nothing but Cj and then Vj, which is nothing but so this is equal to this, and this is equal to Cj times norm of Vj square, okay, as the product of Vi, Vj equal to 0 if I not equal to j. So the other term vanishes, right? Then what will be the Cj coefficient? Coefficient is nothing but of inner product of x and Vj divided by norm of Vj square. That we actually telling, right? So thus this Cj is nothing but inner product of x with Vj divided by norm of Vj whole square, right? And hence x can be written as summation of inner product of x with Vj with norm of, oh my god, norm of Vj square into Vj, right? So the advantage is that so this is dummy sum. It's dummy variable, right? J can go on to k or I can go on to k, doesn't matter. Okay. So what is the advantage in inner product space? That if you have linear combination vector with a linear combination of orthogonal sets, then the coefficients of that combination you can easily find out. Okay, and these are actually called Fourier coefficients. And okay, so this is true for any orthogonal sets. In particular, if B is a basis, then also is true. Okay, so if B is a basis, is an orthogonal basis, then also it is true. Okay, then also this identity is true. Okay. Okay, so now maybe we can have a direct corollary that in addition, if you have orthonormal things, then what happens? So corollary, if B is an orthonormal basis of B, then every element of V can be written as, so you choose any element x, it will be written as summation x vi of I equal to say 1 to k. So I'm assuming that this B is finite dimensional. If B is not finite dimensional, then it will have some finite meaning k. Okay, this I'm assuming. Okay, and that is obvious because orthonormal means what? Orthonormal means that Vi norm, that is the norm is 1, right? All the norms 1. Norm square is also 1. So from previous theorems, and this denominator will be 1, and then this is done. This is obvious, right? Okay, so yeah, so these are some of the properties of orthonormal set. We will prove many such properties. In fact, we can say that for finite vector space or inner plus space, such orthonormal basis always exists. That we will going to prove maybe in next class. Before that, maybe we can have some example. Okay, so now suppose we have vector space V, which is R3, and in last lecture recall that we have orthonormal basis, which is 1 by root 2 into 1 1 0, and then 1 by root 3 into 1 minus 1 1, and then 1 by root 6 into minus 1 1 2. Okay. Now question is that so this was already discussed in last class. So can we actually so this is obviously also basis, and this is also orthonormal. So this is orthonormal. So this and orthonormal basis of R3 over R, obviously. Okay. Now you can ask that whether you can actually write down any such any vector in terms of these vectors or not. Okay, and the answer is yes. For example, and then you can easily compute it and directly, right? So, for example, suppose you have to write down the vector say 1 1 1 in terms of this basis. Then what will happen? You know that this will be suppose this is my vector v, so this will be inner product I equal to say 1 2 3 and then v with okay, so let me write down the name of these also. Maybe this is v1 v2 and v3. Then this is nothing but some is going to be I yeah and vi, and these are orthonormal, so norm of the i's are always 1, right? Now what are those vectors, those coefficients? So you compute this coefficient 1 1 1 and product of that with the first one, which was 1 by 2 into 1 1 0. But this is real number, right? So the computer will be also same. So this will come out, and then this one is what? This one is 1 into 1 1 and 1 into 1 1. So this 2. So this is nothing but 2 by root 2. Similarly, so this is your this first one, first coefficient, right? And second coefficient is what? Second coefficient is 1 1 1 and with 1 by root 3 into 1 minus 1 1, right? And this will be what? This will be again, so 1 into 1 1 1 into minus 1 minus 1, so this is 0, this is 1, so this is 1 by root 3. Okay, and the third coefficient is what? So this was all your C1 and C2. The third one is what? So 1 1 1 and 1 by root 6 times what are the vectors? So minus 1 1 2 minus 1 1 2, and this will be 1 by 6 outside, and 1 into minus 1 is minus 1, 1 into 1 is 1, so that will cancel 1 2 2, so this is also 2 by root 6, so this is your C3, right? And then so now see you can easily find the coefficient so quickly, so you can write down hence this 1 1 1 can be written as 1. So what was the first one? 2 by root 2, 1 by root 3, 2 by root 6. Okay, so 2 by root 2 times first vector. First vector was what? That was 1 by root 2 to 1 1 0, and this second one was 1 by root 3. So 1 by root 3 times second vector was 1 minus 1 1 and plus last one is what? 2 by root 6. 2 by root 6 times 1 by root 6 into minus 1 1 2, right? Now so this is what? This is 2 so 2 get cancelled, so this is 1 1 0, the coefficient is 1, and then 1 by 3 times 1 minus 1 1, and this is 2 into 2 by 6 means 1 by 3 times minus 1 1 2. Now you see that is exactly, this is the linear combination of the vector 1 1 1 in terms of the basis element, right? Also rather I must write down basis element. So this is the linear combination. This is I wrote to check actually. This is the linear basis element. So to check, so you can check that this is correct formula because 1 by 3 minus 1 by 3 is 0. So this is first coordinate is 1. Second coordinate is minus 1 by 3 plus 1 is 0. So this is 1. And third one is here 0 and here 1 by 3, 2 by 3. So this is 1 exactly. So you can check that. Okay. Okay, so this is some of the properties of orthogonal set, and in next class we will discuss one of the most important theorem called comes with orthogonal theorem. Okay, so I will stop here.